Hello everyone. My name is Toby and welcome back to my channel. This is Promoting Safety Engineering. And yeah, I know I've been MIA for a while. I've been so busy doing various stuff and so yeah. Anyway, I'm back now. And so I want to drop a couple of videos and welcome back to the channel. This is Promoting Safety Engineering and we do everything safety engineering and process safety and loss prevention and just safety in general in the oil and gas and the likes. Okay, so today I'm going to be talking about blowdown and shutdown and depressurization. It's part of the series which I started making about getting to our fire and explosion risk assessment, quantitative risk assessment, and a safety case. So it's part of that journey. So the last video I did was a fire and gas detection video, which explained the different kind of flame, heat, smoke detectors, and yeah, I want to tie that into this, and we'll go further ahead. Yeah. Okay. So firstly, don't forget to subscribe and like the videos. Thank you. The likes help us a lot. But okay, so I want to give a quick, like a rundown overview of this is a compressor system, and I want to explain how it works so that you just kind of have that idea. It's also good knowledge. So this is a compressor system. This is a scrubber, is a vessel, vertical vessel, and this is a compressor, and this is a cooler, a fan cooler, and then okay, so it's a three P&IDs, and I'm gonna talk about the layout, and the P&ID, and also the cause and effects drawing. I'm gonna try to link them all together. Okay, so the way this operates is gas. Whatever comes in here is a mixture of gas and some liquid and fluid. So this compressor system, this is a vessel. It goes, the feed goes into the compressor. What you're not so bothered about what comes out here, because this is a compressor system. A compressor is like a pump for a gas. It takes gas from low pressure to higher pressure. So let's say so this vessel operating at about 0 point something bar, gas comes in here. You want the gas at a higher pressure, maybe because you want to sell it or you want to deliver it to a certain customer or to a certain equipment that needs the gas at a certain temperature and at a certain pressure. So this is the kind of system you would have to do that. You would need a compressor and some fans. So say the gas comes in from here and the liquid. It's going to be mainly gas, or it could have liquids in it, but mainly gas. It comes in here, the fluid or the liquid goes to the bottom, and the gas goes out the top. The gas that goes out the top goes straight into the compressor. Remember, compressors don't like liquids. They don't want liquid. You don't want liquids in this. You don't want, because it's gonna damage it. So it's gonna be broken in no time if you have fluids in there or liquids in there. So what you want to do is trap or capture all the liquid here, and whatever is entrained in the gas, these are demister pads that would trap whatever gas is in here, and it would just it would trap whatever liquid is entrained in that gas, and just the gas comes out here. Now when you come here, you can see that this suction scrubber, this is the suction scrubber, it's before this, and then you have a discharge scrubber at the other end. This takes up, this operating is 0.2 bar, and the operating temperature is 32 degrees Celsius. So that's what comes out here. But when it goes into this compressor, it's compressed to a higher temperature, but you cannot compress gas to a higher temperature without the pressure increasing. So without the temperature increasing. So the gas that comes in here is compressed to a higher pressure, but in that compression process, the temperature also increases a lot. So you would see that from here 0.2 bar, when you go into the compressor, that 0.2 bar in and out comes in at 0.2, goes out at 3.7 bar. But when it hits 3.7 bar, you have to remember that temperature increases also. So the temperature came in at 32 degrees Celsius, and it's going to go out at 134 degrees Celsius. So that's really high. So the gas going out here is much higher. The temperature is higher, the pressure is higher. And that's why you have the pressure gauge, the temperature indicator, the pressure, the trip here, so that whatever process upsets the system can trip. So you have all that here, all the protection. These are all forms of protection to be able to control the process. And then after that, because it becomes very hot, probably where you need the gas to go to, maybe you need it at a much lower temperature. So, but you need it at still that high pressure. You have a fan to cool it down so that the temperature drops, but the pressure is still relatively the same. And that's why when you see the cooler here, you can see that the inlet is 3.7 bar, but the outlet is 3.2 bar. Coming from here, 3.7, it goes to 3.2, and you can see the temperature comes in at 134, but it goes out at 50 degrees. So the temperature drops a lot, but the pressure doesn't drop so much. So that's the trick with it. But the other problem is when this temperature drops a lot, it's kind of what they call like Joule-Thomson effect. When the pressure drops very much, you're gonna produce some liquid. It's just normal. Like anywhere you really drop the pressure of a gas, the liquids form. It's condensation. It's normal physics. So when that happens, automatically you now have liquids in your stream with the gas. So what you do for that is you set up another. So this is a continuation. This is page 1. We go into page 2, and you have another vessel here. So whatever liquid has been formed due to that cooling process gets trapped in here, and you have just gas going out. So as that gas goes out, it comes all the way into another compressor. So you could have a first stage compressor, second stage compressor, all compressing and cooling to make sure that whatever temperature and pressure you want to have at the end, you can achieve it. Of course, this is mainly done by the process people. That's why it's good to have an idea of process before you go into process safety. Okay, so that's more or less in a nutshell how the system operates. Now, I want to go into talking about the topic, the depressurization and blow down, shutdown. So, for a facility like this, you want shutdown valves. Now, shutdown valves, what a shutdown is it's stopping the plant from operating when there's some issue. Either it may be maintenance, you want to do some maintenance, or it could be an accident, or it could be there may be a fire. You just want the plant to stop operating. But when the plant stops operating, you want to make sure that you don't have stuff still moving around, because gas is a very, very, they can move anywhere easily, right? So you want to make sure that you shut them in. You lock the gases and the liquids, and so that they don't flow around in a shutdown. So how you do that is you have shutdown valves. Here you can see for this equipment with this vessel, you have a shutdown valve here on the inlet. You can see that on the liquid outlet. It's different from control valves. This is a level control valve. This is a shutdown valve. The level control valves is part of all this are connected to the process control system. the PCS, whereas this is controlled by the shutdown system. What this does, the difference between this and the shutdown valve is this is trying to control the level of the liquid in here so that it doesn't go so low that it's empty, and then it doesn't go so high that it's too full. That's why it's connected to this high and low. So this is controlling this. It just flow goes up, goes down. If the liquid in this is too much, it opens up and more fluid goes out. If the liquid in this is too low, it closes so that you don't have an empty vessel, because then you would have a gas blow by. That means the gas can force its way into the liquid leg, which is really bad because the systems on the liquid side are much, the pressure, they're not, should I say, rated for a lot of, for high pressure. So you have these shutdown valves everywhere. Well, let me not say everywhere. Well, you have some philosophy to guide you. So this shutdown valves, they're very necessary because when there's a fire, so let me go to my, so let's say there's a fire here, but the fire can, if this fire goes on long enough, the heat from here can affect what's here, and then you would have this blow up. And if you're not careful, it would affect what's here, and that's how the fire jumps around. So what you want to do is, the best way to stop a fire, because what we're going towards is fire and explosion risk assessment and quantitative risk assessment. The best way to stop the fire is to close the feed of the fuel, whatever gas or fluid is coming into whatever vessel that's on fire. You want to make sure the shutdown valves close on the detection of the fire. So when they close, the fire is isolated. It cannot jump around. The fire should die out quickly once it doesn't see any fuel. Remember, you need three things for fire. You need your fuel, you need your oxygen, and you need some ignition. And so, okay, so let me go back to the layout. So what you're trying to do here is lock whatever inventory, whatever fluid, whatever gas is inside whatever place is on fire. You want to lock that in and stop whatever is feeding it. So let's say this, I'm just assuming, let's say this gets its feed from here. You want to make sure this is closed so that it doesn't have any, and this is on fire. If this is on fire, you want to make sure that whatever is bringing this in is closed so that this does not get any more fuel to keep on burning. After a while, the fuel will burn out, and because really, your fire and gas system, your sprinklers, your monitors that spray water everywhere, they don't actually kill the fire. They don't put out the fire. What they do is they cool the equipment around, because this fire can be so hot that it jumps here. It balls up what's in here so much that this blows up. And when this blows up, it's what you call a BLEVE. That's a boiling liquid expanding vapor explosion. Wow, that's a mouthful. Boiling liquid expanding vapor explosion. It's called a BLEVE. So the heat from here can escalate to here. It can escalate to here based on the producing so much heat that everything around here starts popping up, because the gas there and the liquid start boiling up, and the pressure increases and it blows up. So you don't want that. So your shutdown systems should be done in such a way that they're they're connected to your fire and gas detection system. And that's why I did the video of the fire and gas, because it could be triggered by a heat detector or a flame detector, or you could even shut down if there's so much gas in the environment. Like if there's a gas leak and your gas detector picks it, the system might be calibrated in such a way that it knows that there's so much gas and there's likely to be a fire, and it would shut down. But most times it's because there's some fire around that it would shut down. So your heat detectors or your flame detectors will pick it. Now those are connected to your shutdown valves. Your shutdown valves get the signal from your from your fire and gas, or from your fire and gas detectors, or from your from your control room or your shutdown system. It picks it up and it knows that I'm supposed to close, and automatically traps whatever inventory is in here, and so that it doesn't escalate and you don't have it flowing and stuff flowing through the pipes. Now, when this happens, this is very key. There are different types of shutdowns. So that's why on top you see ESD0, ESD2, ESD1 to OSD. So you could have an entire plant shutdown. So depending on whatever is happening, you might want to shut down the entire facility. Maybe the fire is getting out of hand. You so you go to probably an OSD. This most likely this is the highest level. ESD0, and that means the entire plant should shut down. Every equipment around here shuts down. Everything, so that you don't worsen the situation. Now that could happen, or what could also happen is you could have a unit shut down. So this, it could be looked at as a compressor unit. So that may be OSD0. This is ESD0. This is OSD0. So this might be a unit shutdown. So everything here would shut down. But in this kind of plants or facilities, you have like this could have like you could have like four streams of this, like for like, all being processed at the same time, and you have so much other processes going on that you don't want to shut down everything, because maybe there's a little fire here, or there's you might want to do some maintenance on just this part alone. So you want to have a unit shutdown. So you just shut down a little part of the system. All this will be explained in your shutdown philosophy, your blowdown philosophy. All this would be explained in there. So you want to make sure that all this, and then you may just have equipment shutdown, which may be this 3.2.6. It might just be an equipment just this alone. You want to just walk on this, or maybe wherever the fire is, this is the only equipment that could be affected. So you just want to shut this down, and have the other stuff still operating. Although this feeds this, but you get what I mean. Maybe some other things could still be operating on the site. So you could have just that particular equipment shut down. Then also there's what you call a local shutdown. Maybe you're right there by the equipment and you see a problem. You can easily, they should have manual push buttons that can shut down the equipment or the entire facilities. You should have them around. So you may want to do that. So you have different levels of shutdown. And then what's the second thing that I want to talk about is your blowdown. This is what you call BDV, a blowdown valve. BDV. These valves they're connected to your shutdown too, but this don't close. This open up when there's a shutdown, especially when it's involving a fire. This open up because this is on the gas line, right? This is it. It's on the gas line, and you don't want your gas line to be pressurized when there's a fire. You don't want gas in here when there's a fire, because you could have it heat up and rupture. So what you want to do is, you don't want all that gas trapped in here with the liquid. So the best thing to do is relieve it to the flare. So when this close, this open up, but this would only take out gas and it takes it to the flare. So you have a shutdown. All the blowdown valve, this is a blowdown valve, is always on the gas line to the flare. This happens, you can see, I want to take you to another picture of a blowdown valve. Yeah, this is it. You have it here also. They're very important, because what that means is that when there's a fire, you don't have gas trapped in here. You want all the gas relieved, because you have gas in here, it's a problem, right? It could become, it could blow up the vessel. So you don't want to have that gas in here. Depending on how much the fire is, it could cause a lot of problems for you. So you want to make sure that when there's a shutdown, this close and this open up, so that This you just have dead crude, just dead liquid in here, and all your gas goes out to the flare. So the flare, when that happens, of course, the flare would see a lot of fire. You would see the fire really burn bright because there's a lot of gas going there. But you know, your flare is like it's a protection system. It protects. It's for protection. So it's to take all whatever excess gas when there are process upsets or there's shutdowns and the likes, and it's supposed to just relieve everything and burn it off. So yeah, so that's it about blowdowns, shutdowns. But also, I still want to talk about something else, which is called your cause and effects. Now, this is a cause and effect chat. What it does is this is a trip. It's talking about what closes, like what makes these valves close, what tells these valves to close. So for this now, it's part of the process system. So they're called trips. You have them like this is a TZ, that's a temperature trip. This is a PZ, that's a pressure trip. This is an LZ, that's a level trip. So this is a LZHH. So this would most likely, if you have very high level, this trip will come on. And what it does is, if I can follow, so this is how you read the chat. If I can follow, can I see the X? Yeah. So this trip, it's a level trip. It would tell you what it closes or opens. It opens this shutdown valve to a twister unit inlet. It closes it most likely to this inlet. So you have this valve being controlled. There are different trips that would control it, but that's why you have all these X's. But you want to know, like when you're going through maybe the P&ID, your has up. This is just explaining, right? We're not going to go through each one, but let's say this is a level trip, high. So let's say the fluid in here goes so high. So you want to close this down so that this doesn't get any feed in. So let's say this level trip. So let's say this level trip here. Let's just assume that that's what you have here. This level trip. Where's that? Yeah, level trip high. So you want to make sure, was that the one I saw before? I think it was this. So you want to make sure, so it would tell you what shutdown valve it's going to close. That's why you prepare this chart, to know what each trip closes. So this is a low inlet temperature. So remember we had temperatures in here, temperature, trips, and all that here. So let's say you have low temperature coming in, and for whatever reason you know that that's bad for your process. So you would put a temperature, low inlet temperature trip, so that when that's why it's TZALL, when the temperature is so low, you have this shutdown valve closing, and it would tell you, you will be able to find, some of them would have the pages and all that, and with that you can find where exactly that is going to, where exactly this trip, what this trip controls. You can actually find it with that chart. So when you look at this, because this doesn't point you anywhere, because what this might be closing might be 3 pages downwards in the P&ID. So you would not know it from looking at this exactly. But when you look at your like, you can see your temperature trips here, but when you look at your cause and effects chart, it tells you where every trip, what it controls, what shutdown valve it controls. And with that, you know that, okay, can you see this controls a fan, this controls a blow down, you can see this controls a blow down valve, this, and some control a shutdown valve, SDV, BDV, you can see SDV here, BDV here. So it's this chart that tells you what trip controls what, and you can use it to decide how the process should operate. So it's good to have it in a heads up. And yeah, so I wanted to explain this because I'm going to go into isolatable sections, meaning when when there's a fire, you want to have an idea of what's trapped in here and the risk that this can cause. So anyway, that's me on talking about blowdown depressurization. And from that, I'll go into isolatable sections, and then we'll be talking about how you calculate your risk. Okay, so thank you very much for watching today. This is Promoting Safety Engineering. This is Toby, and please don't forget to like the videos and subscribe. Thank you. Do have a lovely one.